Hi. In this lecture, we're going to look at a model that's a favorite of mine, known as the standing ovation model. Now, this is a model that builds off the Grenovetter model. It's just really an extension, but it's going to allow us to sort of think about threshold-based models of participation and peer effects in a little more subtle ways. Why standing ovations? Those seem like a kind of funny thing to study. Well, here's why. Think about a standing ovation. When the performance ends, you don't have a lot of time to decide whether you're going to stand up or not. You've got to make sort of a fairly quick judgment. You're going to clap, of course, right? But then you've got to decide, do I stand or do I not stand? And then after the standing ovation either starts or doesn't start, you've got to make another decision. Do I stand up? Do I follow these people, or do I, stay sitting? So when we think about human behavior, there's going to be different models that we play with throughout the course about how humans act. One model will be that people are optimizing, that they make rational choices in all settings. Well, in the context of a standing ovation, that's probably a difficult thing to do because it's all happening so fast. So instead, what people probably do is they follow rules. So standing ovations are a nice place to sort of get people, it's a nice domain to get people thinking about rule-based behavior, about people following simple rules and then asking how those rules aggregate. So it's kind of like the Schelling model that way, right? People follow rules and they aggregate, and we're going to see what's going to happen. Only here, right, this is a model of, I think of it as like peer effect. Now, why? So when you think of a standing ovation, one way to think about it is as a peer effect, right? Other people stand and then you stand. But what's nice about standing ovations, another thing that's nice about it, is that it could also be information. So what do I mean by that? Well, suppose you're sitting in the theater and you notice that the woman sitting in front of you to the left, is talking with her neighbor, and she seems to know a lot about the theater, about the performance you're going to see, and she seems like someone who's a little more sophisticated than you are. So play ends, and you're trying to decide, how do I stand or not stand? And you see her just pop up. She just pops up. She's applauding like crazy. Well, you figure she's conveying some information that could be useful to you about the quality of the show, and so you decide to stand up. Right? So it's not just that you're copying her for the sake of copying her, like in the Grenovetter model, like with the purple hats. Here you're copying her because you think she's telling you something about how good the show is. Okay, so that's an information effect. So what we want is we want a model that's going to capture these sort of pure effects and information effects. So just like in the Grenovetter model, we're going to have a threshold. There's going to be a threshold in which I stand up, but it's going to be somewhat different. So in the Grenovetter model, the thresholds were the number of other people doing the action, participating in the collective action, rioting, wearing the purple hats. There's some number of other people that I needed for me to do it. Here, the threshold is going to be related to the quality of the show. So what you can think of is, let's suppose shows have qualities between 0 and 100, and your threshold may be 70 or 60. Any show above 70, you stand. Any show below 70, you don't stand. So if the quality is above the threshold, you stand. Quality is below your threshold, you don't stand. But let's make this a little bit more sophisticated. So let's suppose instead of there just being, you see the quality, let's suppose that you get something called a signal. Now the signal is going to be the quality plus some other term, some term E, which we can think of as an error, right? So you don't see the true quality, you see the quality plus some noise. And now your decision to stand doesn't depend on the quality in your threshold, it depends on your signal and the threshold. If your signal's above the threshold, you stand. If your signal's below the threshold, you don't stand. Okay, so that's the model. Well, one more thing. One more thing is, because that was the initial decision to stand, now you've got to decide, okay, after this sort of initial decision, do you stand once you see other people standing? So what you can assume is that you've got some sort of threshold X, right, that says if 10% of people are standing, I'll stand, or maybe if 30% of people are standing, I'll stand, right, and that also affects your behavior. So the rule really depends on just two things. One, your initial threshold for quality, and then two, this second threshold for how many other people have to be standing for you to continue to stand. Okay, so that's the model. So now let's think through some of the results we can get from this model. So the first claim is, higher the quality of the show, the more likely to be a standing ovation. Well, why is that true? Well, think about it. You stand if the quality plus the error, which is your signal, is above the threshold. So if the quality is higher, your quality plus your error term is higher, it's more likely to be above the threshold, more likely to get a standing ovation. Again, not surprising. One thing we want from models is we want them to give us results that make sense, right? Basic things that make sense. And then the other stuff, right, may be more surprising, but we want some stuff to really accord with our logic right off the bat, okay? What's another result? Another result is lower our threshold, make our T lower, we're more likely to get a standing ovation. Why is that true? Again, same logic, right? We need our signal, the quality plus the error, to be bigger than our threshold. So if my threshold falls from 70 to 50 to 30 to 20, I'm more likely to stand up, right? Makes perfect sense. Result 3, the lower X, remember X was the percentage of people who have to stand for me to stand subsequently, then there's going to be more ovations, right? Okay, that makes sense as well, right? And the logic is you stand if more than X% stand. So if X goes from 60%, if you need 60% of people standing down to 10%, you only need 10% of people standing, then you're much more likely to get a standing ovation, because if 12% of people stand, then everybody stands up. All right. Now, what would cause X to be big and what would cause X to be small? So this is a cool thing about models. You write down these little variables in terms of stuff, then you can think, okay, what does that mean in the real world? So what would it mean for X to be big or X to be small? Well, that's sort of how willing you are to stand based on other people standing. So big X would mean if you didn't stand initially, you need to see a ton of people standing before you stand. So this would represent people who are really secure in who they are. A small X would mean people who are really ready to jump on any bandwagon, right? So if 5% of people are standing, then they stand. So this X tells us something about the people in the audience, right? Which is an interesting thing to think about. Okay, let's go back to this signal. Remember I said you get this signal S, which is Q plus this term E. What is E? Well, remember I said E is error, right? So I said there's a quality of the show that may be like 55, and you don't see 55, maybe you see 58, 52. So it's variation in what we perceive. Well, another way to think of that variation in what we perceive would be to think of it as diversity, right? If you and I care about different things, we've had different life experiences, we may interpret the theater, the performance, differently than one another. And as a result, what's a 50 to you may be a 60 to me, or what's a 70 to me may be an 85 to you. So because you and I are different, we're actually going to have different qualities. So this E term, right, this Q plus C, we can think of this as either error, or we can think of it as diversity. And so that, why does that matter? Well, it matters because when we think about interpreting the model, like what the model tells us, in the one sense, in the one case, it'll tell us, well, what happens if people have more noise in terms of how they interpret the show? Or alternatively, we can say, what does it mean if the audience is more diverse, right? Okay, so, well, what does it mean? Well, to do that, now we've got to think a little bit. Now we've got to actually sort of do some math. So let's do an example. Suppose we've got 1,000 people. The threshold for all these people, to make it simple, is 60. And the quality of the show is 50. So 50 is less than 60, right? So that means people aren't going to stand for the most part. If there was no error, no variation, nobody would stand up. Okay, so let's do a case first where the error term is really small. So it's 15. Now the mean here is 50, right? And the error term is either between minus 15 and plus 15. So someone's got an error of minus 15 gives it a 35, and someone's got an error of plus 15 gives it a 65. So that's right, 65 there. So all these people below 60, they're going to sit. They're going to clap. They may clap nicely, but they're going to sit because it's below their threshold. So only this small set of people here stands up. So unless X is really small, what's going to happen here is few people stand up, no standing ovation. But now let's increase the variation. Let's suppose the variation goes from minus 50 to 50. Well, now the people get the score of minus 50, right? They're going to give it a score of 0. And the people who get a score of plus 50, they're going to give it a score of 100. Now, once again, the average score is still 50, right? So that's less than 60. So the average person doesn't stand up. But here, all these people stand up. So if we assume people are sort of uniformly distributed between 0 and 100, so they're equally distributed across there, that means that 40% of people will stand up. So what that means is, unless X is really small, as long as X is above, below 40%, you're going to get a standing ovation. And think about it. If you go to the theater and you see 30% of people stand up, you're likely to stand up. So what we get here, when you have this large diversity or large error term, you're more likely to get a standing ovation. Okay? So that's claim 4. If Q is less than T, so if it's a bad show, well, not a bad show, it's not a great show, you're more likely to get a standing ovation if the variance in E is larger, right? And again, that's because you stand if Q plus E is bigger than the threshold. If there's more people with big E's, you're going to have more people stand, and then it's more likely to cascade into a full-blown standing ovation. Okay, so let's think about what would cause E to be big. Well, one thing would be the audience, right? So if you have an unsophisticated audience, maybe they don't get it. I mean, some people would think it's great, some people think it's bad. You're just going to get more variation. Or if you have a diverse audience, right? If you have people from different backgrounds, you're going to get more variation. The performance itself could matter. If it's really complex and hard to figure out, that could cause variation. Or if it's just multidimensional, if there's lots going on, that could cause more variation. So different attributes of the audience and the performance could result in more variation in that E term, which could lead to more standing ovations. So let's think about what we know. What did we learn? Higher quality show, more likely to be a standing ovation. Not a surprise. Lower threshold for standing, right? More likely to be a standing ovation. Again, not a huge surprise. Sort of people more willing to stand up, jump on the bandwagon, lower X, more likely to be a standing ovation. Larger peer effects, what do I call that? And the last thing is like more variation. If there's more variation, more diversity in that error term, then more likely to get a standing ovation. So here we got these 4 sort of nice results that help us understand when we're going to get standing ovations, when we're not. Now you could say, how much did the model help us? Well, my guess is that if you just thought about standing ovations without constructing a model, you might figure out, yeah, better shows get standing ovations. People more willing to give standing ovations are going to give standing ovations. And if people are more susceptible to influence, you're going to get standing ovations. But you probably wouldn't have gotten this one. You probably wouldn't have gotten more variation. Now, you might have if you learned the Grenovetter model, right? But most likely, you wouldn't have had it. Now, that's the simple standing ovation. Let's ramp it up. Let's have some fun, right? So let's do an advanced standing ovation model. Now, I used to give the standing ovation model as this assignment for students. And they construct models a lot like the ones we just did. Now, what's funny is if you don't give it to a student, if you just ask somebody in the street to start describing a standing ovation, or just going to the theater, they'll include 2 things that weren't in the model. Now, modeling requires leaving things out, but here's 2 things that almost everybody leaves out of a standing ovation model. The first one is the theater itself, right? I mean, you're actually in a theater. You're not in our model. We just have had these people who sort of saw everybody, but that's not true, right? Other thing is this: most people, when they go to the theater, they go with a date or a group. I mean, sometimes you go alone, right? If I'm traveling to New York or something without my family, I may go to the theater alone, pick up one cheap ticket. But for the most part, when I'm sitting in the theater, I notice that most people are there in groups. Okay, so now we can ask, do these things matter? I mean, these are features of the real world, not in the model. Do they matter? Well, let's see. Let's look at the auditorium itself first. Okay, so here's the front, right? Here's the front of the auditorium, and here's this performer with a funny hat conducting the orchestra. And we want to think, does it matter? Well, let's think about it. So if you're sitting here, if you're sitting in this spot, you don't see everybody after the standing ovation starts. You may only have some sight lines, right? So you get some sort of cone in which you can see who's standing and not standing. Let's think about why that might matter. Well, suppose, I'm sitting here, I have this cone, I'm sitting here, I get this cone, here I have that cone, here I have that cone. So you see that there's small cones and there's big cones. Let's think about the difference between those two. So what's a small cone person? A small cone person is somewhere in the front. They don't see anybody, right? But notice that almost everybody sees them. So they influence everybody, but they're not influenced by hardly anybody. They're like celebrities, right? They're celebrities who, we all pair with the celebrities do, but they don't care much, but we do, right? Now, what about people in the back? With people in the back, they can see almost everybody, right? But almost nobody can see them, right? Anybody sitting in here, nobody can see these people, right? They can't unless they can look through the back of their heads or they turn around or something. Well, these are more like academics. These are more like people like me. Spend a lot of time studying how the world works, but not that many people pay attention to what we say. More people care what Oprah, right, or Ashton Kutcher says than what I say. So as a result, even though we have a better sense of what's going on, right, nobody listens to us. Well, let's think about the ramifications of that. What that means is, what we'd like to get a standing ovation if the performance was good, and we'd like to not get one if the performance was bad. But what's happening is everybody's queuing off these celebrities who really don't know what other people think, and nobody's paying attention to the people in the back who really do know what everyone thought. So this means that maybe the system isn't going to aggregate as well as we'd like it to, right? So maybe we're not going to get the right answer as often as we expect to. Okay, what about dates? What about the fact that, hey, look, got a date, going to the theater. How does that matter? Well, think of this with respect to the X term. Like before I said, I'm going to stand, I'm going to look around, I'm going to stand if, X% of people are standing up. But once I've got a date, if she stands up, then I'm probably going to stand up. So what this means is, if you think about people in groups or in pairs, if one person in that pair stands up, then everybody might be more likely to stand up, which means that adding groups or adding dates or pairs means that you're going to get more standing ovations, because all it takes is one person in the group to get them both to stand up. That's going to increase the percentage of people standing up, which in turn is going to create more of a standing ovation. Okay, so what do we got? How do we increase the probability of a standing ovation, right? We had the 4 we had before. Higher quality show, right? Lower thresholds, larger peer effects, those are the obvious ones, right? More variation, the unobvious one. And now we have 2 more. Use celebrities. Put people in the front, right? Put people in the front who are going to stand up for sure. So pay somebody in the front to start an ovation. And then big groups. Create groups of people. And then if one of those people in that group stands up, the whole group stands up, and then that causes more people to stand up. So now we've got 6 ways you can cause standing ovations, and I'm willing to guess that like these three might not be things you thought of, right? The people in the front matter more, and that you want to create groups. So the models actually helped us figure things out. Okay, so wait. This point, you can say, okay, Scott, this is all fun and good, but this is standing ovations, not that important. True, absolutely true. But again, we're using this model, right, to help us sort of make sense about rule-based behavior in environments where there's peer effects. One of the reasons we construct models is for fertility. So once we construct a standing ovation model, we can use it someplace else. But where else can we use it? Well, we just studied, right, collective action problems or, participation problems in political uprising, riots, and things like that. And that looks a lot like the standing ovation model. And now you can think of who are celebrities, right? And what does it mean to have big groups in that sort of context? Well, the celebrity would be someone who's maybe got a lot of influence on other people. So if you want to start a political uprising, you need those sorts of people. So this tells us something about that. It also works for things like academic performance. Suppose you've got a school that's underperforming and you want to sort of have people lift themselves up, right, to work harder. How do you do it? Well, you can think we need to sort of raise quality, lower these sort of thresholds of the barriers for people to sort of engage in this productive behavior. You can do things like use celebrities, right? And you can even create groups of students who work together to all do well, right? And that may cause other people to do well. Urban renewal, right? You could think of each one of these people each one of these boxes, instead of it being a person standing up, you could think of it as someone fixing up their house. Now, what's interesting here is, let's go to that sort of variation idea. Well, you could think, we want to improve some city. Let's give everybody $1,000 if they'll fix up their house. Well, it could be that nobody does it because it doesn't push anybody above their threshold to fix up their house. But the variation idea says if we give a handful of people a lot of money to fix up their house, they may do it, and then that could cascade. In fact, a lot of people who study urban renewal push that sort of logic, that you should target particular areas where people are likely to do it, get things started, and hope the process log rules. All right? Fitness and health. If you want to get a group of people, a society even, to become more healthy, that's a lot like a standing ovation. You need some people to do it, and then you hope other people do it. Now, that could be peer effects, right? I see other people being healthy. I want to just copy them. Or it could be information. I see them acting healthily, engaged in fitness, and then I think, you know what, they're doing better than I'm doing, so maybe, they seem happier and healthier, so I'll copy what they're doing. Even like, right, this online course. If I want people to sign up for this online course, it's like a standing ovation model. Each person's deciding, do I stand up or not? Is the quality above my threshold, right? So if I want people to take the online course, I can draw lessons from the standing ovation model and think about how do I do it, by using celebrities. And that's in some sense what I did, right, is I tried to get a lot of my friends who are celebrities within the academic world to say, hey, this is a cool course. All right, so that's the standing ovation model. It's a peer effect model, but it's also this sort of information model. And it explains, again, why we see groups of people all doing, similar stuff, right? Because we see other people doing it, and then we copy them, and this tells us sort of when we're likely to see it, right, and when we're not likely to see it. Okay, thank you.